Yet another conservation of energy problem. But this time, should be getting the hang of this picture. There's the ramp here, same height, same everything, but now this block and the ramp have some friction. So the concepts here are that as this thing slides down, all of its energy is not going to be converted to kinetic energy. Some of the energy will be used to overcome the force of friction, or the force of friction is going to do work on the system, and that force of friction is going to take some of its energy and turn it into heat, sound, what have you. So here, the potential energy at the top is going to become kinetic energy and some work done by the force of friction. There will be energy lost to the environment. Energy lost to environment as heat. That's supposed to say heat. Heat. Okay? Makes sense here. We have to figure this out first. So the work done is force in the parallel component of the force times the displacement of it. Here, the friction is going to be in line with the ramp, and the ramp, right, the force of friction is going to be this way, and the block is going to be moving that way, so we don't have to worry about, they're all parallel, there's no extra pieces there. And so, and the displacement is in this direction, so they're all parallel. So everything there makes sense. So it's all the force of friction and all the displacement. But the force of friction, recall, is mu times the normal force. The normal force is not the same thing as the object's weight, right? There's the weight down here, but the normal force is only a piece of that. We take that weight, we break it up into two parts. The normal force is the weight times the cosine of the angle. That angle and angle are the same. This is review from months ago, but you can't forget any of this stuff. So, all right, what is the normal force? The normal force is going to be mg cosine theta. So we're going to get mu, we're told is 0.2. The force of friction equals 0.2 times mg cosine theta. That's the normal force. So 0.2 times mg, the weight of this thing is going to be 49 newtons, right? Times the cosine of 37. Cosine of 37, so 0.2 times 49 newtons times cosine of 37 is 0.8. And we do all that math. 0.2 times 49 times 0.8, 7.84 newtons. That is the force of friction. Well, the work done is the force of friction times the displacement, so 7.84 newtons times the 20 meters that slides down is 156.8 joules. That is the work done by the force of friction. That's key. So our gravitational potential energy is going to become kinetic energy plus the work done by the force of friction, or mg delta h. That's been the same for, this is still the same angle, so the delta h here, you should remember, is still 12 meters. So mg delta h, 5 kilograms times 9.8 meters per second squared times 12 meters, 588 joules becomes 1/2 half mv squared plus 156.8 joules. So 588 equals really 1/2 5 kilograms times v squared plus 156.8 joules. Bring that to that side. 588 minus that 431.2 joules equals 1/2 5 kilograms v squared. 431 divided by 2.5. We should end up with 172.48 meters squared per second squared equals v squared. And we get 13.1 meters per second equals v. All things considered, not too hard. But you have to remember things from a long time ago. You have to remember the how to get the normal force on an inclined plane. You have to remember the force of friction, coefficients of friction. Lots of things you're not allowed to forget, which makes it tough.